Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here's information about online seminars and study manuals for exams P, FM, IFM, and LTAM that I offer. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help-ISU-actuary. Here's a problem for today for exam LTAM. You are modeling the mortality improvement in a group of annuity holders with an average age of 75. Now remember that mortality improvement stands for mortality declining, so it's really longevity improvement for people whom we are studying. So just remember that that's the meaning of it, that mortality is improving when there's less and less of it over time. For people of the same age, you have probability of dying declining. That's the nature of mortality improvement. You are using the Cairns-Blake-Dowd CBD model specified below to describe the logit of the mortality rate. So the natural logarithm of q of xt. And it's of the form kt1 plus kt2 times x minus x bar. And kt1 is equal to kt minus 1 plus c1 plus sigma k1 zt1. And kt2 is equal to kt minus 1, 2 plus c2 plus sigma k2 zt2, where zt1 and zt2 are standard normal random variables with correlation rho equal to 0.3 within a given year, but are independent from year to year. The fitted parameters from the study are k 2018-1 equals negative 1.9, k 2018-2 equals 0.3, C1 equals negative 0.03, C2 equals 0.001, sigma K1 is equal to sigma K2 is equal to 0.02. 1 point, part A question, describe one advantage of using a stochastic mortality improvement model over using a deterministic model when modeling a block of policies such as annuities. Part B, part 1, show that the mean of LQ, so natural logarithm of Q, is of 72 2019 is to the nearest 0.1. You should calculate the value to the nearest 0.01. My apologies, I had a typo here. It should be that this LQ of 72 2019 is negative 2.8 to the nearest 0.1. You should calculate the value to the nearest 0.01. Part 2, show that the standard deviation of LQ of 72 2019 is 0.06 to the nearest 0.01. You should calculate the value to the nearest 0.001. Part C, calculate E, expected value of Q of 72 2019 over 1 minus Q of 72 2019. Part D, calculate the probability that P of 72 2019, and P, of course, is 1 minus Q, the probability of survival, is greater than or equal to 0.94. E, your colleagues suggest that you consider using the CBD M7 model rather than the original CBD model to describe the mortality improvement of this block of policyholders. Describe one advantage of using the CBD M7 model rather than the original CBD model. And here's the solution. So we should note that the problem uses inconsistent notation for the k parameters, unfortunately, but we need to be just patient about this. It's implied that they mean the same thing, basically. Stochastic mortality improvement models allow us to examine and assess the impact of random variation in the underlying mortality rates in our models. Stochastic models still have parameter uncertainty, and such parameters would have to be estimated, but they allow us to get an idea of how much impact the uncertainty of the mortality model will make on the results, or to the results. Well, on is probably better. Deterministic mortality improvement models cannot do any of this. They are not designed for this. For part B, we have from the basic properties of the model and the parameters given that LQ of 72 2019 is equal to K 2019-1 plus K 2022 times 72 minus 75, where K 2019-1 is equal to negative 1.9 minus 0.03 plus 0.02 Z 2019-1, and K 2019-2 is equal to 0.3 plus 0.01 plus 0.02 Z 2019-1. And apologies, again, I had a typo. This K2 in the second part of this formula on the right-hand side, that should be K 2019-2 times 72 minus 75. So that LQ of 72 2019 is negative 1.9 minus 0.03 plus 0.02 Z 2019-1 minus 3 times 0.03 times 0.01 plus 0.02 Z 2019-1, and because 72 minus 75 is negative 3, and that's equal to 2.833 plus 0.02 Z 2019-1 minus 0.06 Z 2019-1. Now note that since both Z 2019-1 and Z 2019-2 have normal distribution, so does LQ of 72 2019. Now since expected value of Z 2019-1 is equal to expected value of 2019-2 and 0, we have the expected value of LQ of 72 2019 equal to the expected value of that expression for it that we just wrote a moment ago. And as you can see, the last two terms are 0 in terms of expected value, so this is just negative 2.833. Then we know that the variance of 2019-1 is equal to the variance of 2019-2, and it's 1, and the covariance of the two is equal to 0.3 times 1 times 1, so it's 0.3. So that the variance of LQ of 72 2019 is the variance of the expression we derived for it. Now the constant number, negative 2.833, doesn't have variance, or doesn't have covariance with any of the other variables. So its variance is 0, so we can disregard it, and this is just a variance of 0.02 Z 2019-1 minus 0.06 Z 2019-2. And that's equal to 0.02 squared times 1, which is the variance of Z 2019-1. So 1 multiplied by it is just 0.02 squared, plus 0.06 squared, and a plus because you square it, so it's really negative 0.06 squared, but that's the same as 0.06 squared, minus 2 covariances, multiplied by the coefficients of 0.02 and 0.06. Now minus actually comes from this negative 0.06, whichever way you look at it. This is minus 2 times 0.02 times 0.06 times 0.3 we derived a moment ago for the covariance. So this is the variance, and the standard deviation is the square root of that, and that's approximately 0.057713. Now, based on the work above, LQ of 72 2019 is normal with mean negative 2.833 and variance 0.0328, or normal with a mean negative 2.833 and variance equal to the square of its standard deviation, which is 0.057713. And therefore, recall that this is effectively the definition of LQ of xt. E to the LQ of 72 2019 is equal to Q of 72 2019 over 1 minus Q over 72 2019 as a log normal distribution derived from this normal distribution, the same parameters, and this in turn implies that the expected value of this expression is e to the negative 2.833 plus 1/2 times 0.00328. That's from what we know the expected value of log normal distribution is. That's approximately equal to e to the negative 2.83136, which is approximately 0.0589327. Now note that logit and logarithmic functions are monotonic, so that the probability that P of 72 2019 is greater than or equal to 0.74 is the probability 0.94, I think I said that, I'm sorry, is the same as probability that Q of 72 2019 is less than 0.06. That's the same as probability that Q of 72 2019 over 1 minus Q 72 2019 is less than 0.06 over 1 minus 0.06. That's the property of monotonicity of the logit function. That's equal to the probability that the natural logarithm of the left-hand side is less than or equal to natural logarithm of the right-hand side. This is the probability that LQ of 72 2019 is less than ln of 0.06 over 1 minus 0.06. Now, we just know that this random variable we have here follows the normal distribution, so this has got to be phi of ln of 0.06 over 1 minus 0.06 minus the mean, which is negative 2.833, divided by standard deviation, which is the square root of 0.00328. That's approximately phi of 1.43. Of course, phi is the cumulative distribution function of the standard normal distribution. And then from the table on the normal calculator given on the test, you have this to be equal to 0.9236. Now, for part E, the CBD M7 model has an additional model term, G subscript x plus t, that is meant to describe a cohort effect. So, cohort effect is the situation where people born in different cohorts at a specific time have these variations in their mortality that are not part of the long-term trend we're studying. They're just random within the cohorts. Modeling a cohort effect is not possible in the original CBD model, so if we want to include it in the model, we use CBD M7 as a better choice. Another advantage is that the CBD M7 model also includes a quadratic age difference term, which may produce an improved model. Please remember this is copyrighted material. The problem itself belongs to a society of actuaries. The solution is mine. Good luck in your studies and good luck on the test.